Hi, everyone. It's great to be here, and I'm really looking forward to this topic on the P4 Expert Roundtable series. This is a moderated panel on the topic of P4 use cases in programmable switching. This is a panel discussion with Guy Caspary from Cisco, Arkadiy Shapiro from Intel, and Paola Grosso from University of Amsterdam. This is Prem Jonnalagadda. I'll be moderating the panel, and I'm really looking forward to this discussion and presentations from the panel members. So without further ado, I'll hand it over to Guy. Guy?
So I hope everyone can see the first slide. A few words about me. I've been in the networking industry for almost 20 years, I think. I started at EasyChip, moved on to Dune, to Broadcom, to Liba, and now I'm with Cisco. My career is with switching silicon, and that's what I will talk about. And I'm also one of the founders of Liba Semiconductor, where I dealt mainly with the NPU, which is one of the things that interests us today. So let's dive in, and I will talk about Silicon One, which is not a device, and it's an architecture that is targeted to span a broad the full networking market. So the vision of Silicon One, in a nutshell, it's a single silicon architecture for all market segments. That was the vision. And the problem that we were seeing in the last, I would say, more than 2 decades, a decade or a decade and a half. So we saw that silicon devices addressed two different use cases, two main different use cases. One is routing, and the other is switching. We saw that switches were high bandwidth devices, low power consumption, usually low latency, targeted for the data centers and later for the cloud. And routers were more on the enterprise and the service provider side. They were with a richer feature set, sometimes programmable. They had deep buffers and they had very large scale. And we started to see that the industry in fact, diverged into 2 distinct markets, and each market had its own unique architectures, unique systems, unique software. Sometimes we could see that we have 3 product lines, sometimes 2 product lines, and that was the problem when we started Liba Semiconductor 6 years ago. That was the problem that we wanted to address. So this presentation will be more of a story, okay? We will see where we started and how things developed over time, and I will try to highlight the part of programmability in P4 in what we were doing. The Silicon One vision is not only NPU and not only programmability. It's also traffic management, queuing, fabric design. Here, we will focus on the NPU. So we actually started 6 years ago. And from the beginning, we identified that programmability is a must. I personally saw that in order to chase the changing market, we had to have highly configurable devices. So when we started with a clean sheet design, we said we must have programmability. The reasons, among others, that not the only reasons, are first of all, feature support. Having a programmable device allows for faster software development, okay? Because you know that software, you write a line of code, you test, everything is okay. In Silicon, you must tape out, and only then you can, and after tape out, you cannot make any changes. You also have a longer life cycle of adding features. You can add features pre and post Silicon. And of course, it's easier in many cases to fix bugs or to add workarounds. Another important reason for programmability is broad market applicability. A fixed function device needs to support the superset of all functions, which is usually a heavy Silicon imprint. And in each market, only a subset is used. With a programmable device, we can, well, there are actually two options. One is to load a different code image for each market segment. And the other is to have a single code image, but not execute all of it. I will touch on that later. And of course, another important thing is maintainability. What I mean by this is that it is much easier to understand, maintain, debug, teach a high-level code than RTL. When you want to explain to a new designer or to a new programmer the behavior of the device, it is much easier to give them a piece of code, of high-level code, than to give them RTL. Okay? So why did we choose P4? So in the development process, we did several tasks in parallel. Again, if we look at the way devices are usually developed, switching devices, we see that we have the architecture group defining the RTL or defining the design. Then we have designers, then we have tape out, and then we have software development, and then we have the OS development. And when you get to the end of this chain, things change. You learn stuff that you did not know when you did the architecture. Here, from the start, we did all tasks in parallel. We coded the high-level application that covers all markets. We did the architecture design. We developed the tools, and we also developed the SDK. All of these actions were done in parallel. And this allowed us to balance each one of these activities. And we started with C, but we found out that it is too general. Not everything that we could code in C, we could compile or we could implement. It was also easier to think in C when trying to write a networking application for a switching Silicon. There is a sentence that I like by Ludwig Wittgenstein, which says, the limits of my language means the limits of my world. What I understand from it is that the language that we have, the concepts that we have are the ways that we think, are the way that we think. So in order to program a switching or routing Silicon, we must have the correct language. What we saw over time, and this is not just from work on Silicon One, but also from our previous experience, was that the match process or match action paradigm is inherent to networking. At the same time, we saw the work, there was the initial paper on P4, and we decided to adapt it as a base. We added some of our enhancements to it to make it easier for us. It was a P4.14 at the time, and in those semantics, you couldn't do A equals B. You had to put it in an assign clause, and there are other little details that we added because we were engineers and we wanted life to be easier for us. So a few words about the NPU architecture. The NPU contains an array of processing engines. The processing engines are run to complete, and of course they are P4 programmable. And in our vision, there is one code image which covers all markets, and different flows execute different parts of the code, or different parts of the application. And the architecture, again, I'm not talking about a specific device, I'm talking about the architecture, allows for different numbers of processors, and this allows for, of course, for performance and feature scalability in different devices. So let's talk a bit about why run to complete. I think this is novel to the P4 community, so it may be of interest. So for each packet, we spend the exact amount of cycles, latency, and power required. Now, this is an important concept, especially when you want a single architecture that can target complex applications and simple applications. If you want a single device that can span several market segments. A very important feature that stems from this, aside from the big picture of routing versus switching, a very important feature is that very complex but low bandwidth flows, for example, control packets, have a negligible impact on performance. Okay? Usually we have less than 0.1, 0.01, whatever percent of the traffic which is controlled. These control packets usually require a lot of processing. In the big picture, they do not impact the full bandwidth of the device, and they don't affect the architecture. However, also in more regular conditions, there are big advantages for the run to complete architecture. Let me show you two examples. So this slide compares the Silicon One architecture with a pipeline architecture. So for simple processing that has only one stage of real activity, we see that a run to complete architecture simply executes one stage. We can see that the pipeline architecture takes longer. So in Silicon One, we have the latency and power of one stage. And in a pipeline architecture, we get the latency and power of n stages. So this is obvious. For example, if you design a switch for VXLAN routing, it will, in a pipeline architecture, it will spend a lot of time just for bridging. It will waste time when it needs to do just bridging. Another example is when we have n+1 stages. Imagine that you designed a device for, let's say, VXLAN bridging, and someone wants to add routing. They want another stage routing above VXLAN. In the Silicon One architecture, we will, let's see the end stages. So in the Silicon One architecture, the +1 is simply another cycle through the NPU. In the pipeline architecture, we actually have the latency of 2 end stages, and many architectures do a full recycle, so we get a 50% bandwidth reduction. In a run-to-complete device, the only hit is PPS. Okay, and again, it's at the ratio of 1/n+1. Now, another feature for run-to-complete, at least from my point of view, is a natural and efficient coding. If, for example, we look at the flow of a bridge router that also does tunnels, in pipeline architecture, we'll have to go through Ethernet termination, tunnel termination, and then bridging on routing depending on the layer that we reached. The run-to-complete architecture allows us to inject or to add more paths to the flow. For example, at the Ethernet termination stage, we can identify that the packet arrived on a layer 2 subport that does not support routing, and then do bridging. We do not have to test for tunnel termination. We don't have to waste cycles or latency in the tunnel termination stage. If, for example, the packet arrived on a layer 3 subport, what we call a router port, that does not support tunnels, of course, we can go directly to routing. So we can see visually that the processing is very efficient. So the culmination of our work is this Cisco Silicon One. And Cisco Silicon One is an architecture. To the best of my knowledge, it's the first architecture that from the start serves several different market segments: service provider, web scale, data centers, and enterprise. All are covered by the same architecture. I think that this is a first. We are not talking about the TM today, but at least from the NPU, I think that programmability and the other features that we added allowed us to do this. We now can do routing at the same performance in terms of bandwidth and power as switching. And I think that even more important than that is that when we look at the future, systems and products will have a consistent silicon architecture, and they will have the same user experience across the whole network. Meaning that a guy that is familiar with a routing system will also know how to work on the switching system. The operating expenses for network engineers, for the whole infrastructure, are greatly reduced and much more efficient. I think this is the big advantage or message. Apart from having one silicon, etc., programmability, that's less interesting. I think that saying that everything from the user point of view, all markets are identical, I think is a very important message. The first device, I think it was announced end of 2019, but I'm not sure. It's called the Q100, Silicon One Q100. I think it's the first routing silicon that breaks the 10 terabit per second network bandwidth. It doesn't compromise capability, features, etc. I think it's great. And I think that it demonstrates many of the architectural targets that we had. It's one device that supports a fixed switch or a fixed router, and it scales up to a distributed router with a petabit scale. We can see here that the device can be used as a standalone processor, as a line card processor, as a fabric element, with all with optional deep buffers. And I think the last tagline here is important. All of these uses are accomplished with one unified forwarding code and the SDK. And I think that is the big message here. Of course, we also have systems to go along with that. That's the Cisco 8000 series. I think it was announced at the same time. And I think it demonstrates the applicability of all that I've been saying, okay? Because it's a common architecture, also from a system point of view. Again, the silicon is just the bottom building block. Above it, we have the software, the microcode, and the SDK, and the OS, and the systems. And if you don't have the core in such a way that it lends itself to a common definition, you cannot achieve this. So we have the Cisco 8200 series, which is it's a fixed platform of 10.8 terabit per second, and we also have the 8800 series, which are modular chassis spanning from 8 to 18 slots, and from 115 to 260 terabit with the Silicon One Q100. So that's like a history. This is where we started, how we went along the way, and without programmability, we couldn't have done it. P4 is the vehicle that we chose to use, again, because it contains the elements that are important for networking. Now, Prem asked me to talk a bit about how we used programmability, except for the big picture. And I cannot talk about specific customers and specific features that we added to customers. I can say that we are constantly adding features to the systems I just described because of customer needs. But I wanted to touch on two items that are interesting, and they were not something that, it's not something that we defined as a goal, but it's something that once we had a programmable device, we could do. So the first is the silicon verification and validation, pre and post silicon. What you want to achieve is you want to exercise many resources inside the device. And the way we chose to do it is to code a dedicated P4 application for verification. And we inject, with this application, we injected non-standard packets that we defined that contained a set of commands for the device. For example, the path that the device, that the packet should flow through the device, the resources to exercise, how many lookups to do, how many counters to increment, which meters to apply, etc., etc. And if you think about it, it's a very convenient vehicle to do pre and post silicon validation. Okay, the device comes to the lab. You want to see that you can do this and that number of lookups at line rate instead of programming the MAC table or the LPM table and going to a full Ethernet application. You have a very minimal application and you only debug the lookups. You don't debug the other stuff. So that's one use case we found for, apart from the big picture. Another interesting example is power measurement. We had a customer that did not believe our power numbers. And he said, I want to inject a very specific a flow of Ethernet packets. I want this flow to have a specific flow through the ports, to go into N ports and out of Y ports, and I want it to perform specific database lookups that succeed. Do an LPM, for example, to the SIP deep lookup, and I want both of these lookups to succeed. And he said, I don't want to run your full microcode. I am concerned that your full microcode exercises too many features in the device. I want this specific behavior. It took us 2 hours to prototype the application. It took us 2 days to debug and test it, and we delivered the system 1 week later. Don't hold me accountable for the numbers. And the reason is that the shipping and the custom clearance took us 7 days. Okay, mainly customs clearance. So it's amazing that this industry has reached a point where such changes, such features are available to us. Okay, so this is all I have to say. I know it's very brief, and I know there's a lot of details hiding in there that are very interesting. I feel very humbled and excited about this. I'm sure that this will have what we have done in Cisco will have an amazing impact on the industry. That's it. Thank you very much.
Thank you so much, Guy. I really loved the story and the history and how you arrived at the Silicon One architecture, how you chose P4, and those really interesting use cases. Thank you so much.
Thank you.
Okay. Thanks a lot for having me invited here today for this panel session. I was given the chance to present some of the work we are doing at the University of Amsterdam, and I will actually guide you through our work in the next 10 minutes. And let me start by saying that the topic of my short talk will be about high-level usages possible with P4. And in particular, I will touch upon 3 themes that are very important for our research, which are transparency, security, and stability. And I will show you how we actually have used P4 in the past years in our research to try to address these emerging needs of networking. You see here my contact information. If you want to have more discussions afterward for the people that are watching this online, you can just certainly contact contact me, and you can also look at the research we do by following the URL of our group. Now, there was a presenter before me that actually discussed about his work and said programmability is a must. And the second point was that programmability is the way in which you can do coding of high-level applications. And effectively in my presentation, I want to show you how this is possible and why this is needed. So I will actually give you two broad use cases that we actually use as motivators for our research. One comes from science and one comes more generically from society/industry. So the first use cases belong to an emerging need in science applications to move an enormous amount of data from locations where experiments are carried out to processing stations. Could be in the cloud or data centers or high performance computing locations around the world. And what you see, and these are just examples of all things that are happening nowadays or that will happen in the future, like the picture about the telescope that is being built in Chile, is that you have an enormous amount of data that needs to move from A to B, long distances, need for performance, need for stability, need for monitoring, and also need for programmability. Programmability because you have to, for example, in the case of SCARA, the astronomy, an enormous amount of input coming in into your first element of the network, the switching element or whatever element you have ahead of this radio telescope, and you want to be able to do something already intelligent there in terms of the way you actually handle the flows. Could be multicasting or sending them to the appropriate computational stations. So there are a number of emerging use cases that need different approach to networking, not the usual one that we have always done. There are also societal use cases that we see more and more emerging as motivator for programmability. And I think you can lump them through one big umbrella across the motto that personal data is shared nowadays by many parties. So you have an enormous amount of applications emerging, and for example, think of personalized medicine, where it's not about the volume, maybe like in the science application, but it's about the control that you as a user or operator of the network flow want to exercise on the data that moves around. So you can actually carry out personalized medicine if you have in the network ways to program the way that the data is shared to guarantee ultimately the privacy that is required or the kind of level of protection. You also have the same kind of requirement when you move, for example, to logistics use cases. So for example, how different companies that work on the same logistic chain need to share the data. And again, through programmability, you can actually create this flow and these kind of patterns of communication, which are indeed not the traditional switching or routing, as Guy before was talking about, but maybe something else. And finally, you see it also in the whole space of smart cities. So I have here a picture of the University of Amsterdam. I'm pretty sure that the people watching these in whatever cities they are, they've heard a lot about smart cities, integration of IoT and so forth. And again, also this is a use case where you can ask yourself, how do I guarantee the required parameters for this type of data sharing? So these are motivational use cases. These are maybe what was referred before as the high-level applications for which you want to ask yourself, do I need programmability? And we want to effectively ask the question, can we provide additional transparency, for example, in secure data sharing, or security of the data flow, or stability of networks of the future when you have to support these specific use cases? One of the side notes that I wrote down in the slide is that I think what you will see, and you see it more and more as a need, is that you are not trying to do this programmability for the operators. So for the switches, routers / devices owners, but you also to handle more and more the needs of the end users. So it's also programmability, you could also think will open up part of the network or part of the operations to the end users, to the application developers. And I'm thinking here as something that maybe, I don't know if it will be mentioned later in our discussion, in which way, for example, you can integrate P4 and P4 programmability, for example, with virtual network functions. So when you actually have virtual network functions that you could actually allow users to partially control and direct traffic to. So programmability, I see it in our research as enabler indeed for these high-level applications, and also opening up potential potential control into the network for the end users. So this is the motivation of the work and of the research. And the research is broad, long, we have years of experience, lots of boring and less boring research papers you can go and read. So we can discuss them later, but ultimately this is what we are trying to address with the research. This is where we are moving. And maybe one of the questions, why am I invited here? Why am I invited to discuss about this? Well, our research group is fairly known in the international research community, but I think also we have the luxury of being part of large networks, particularly for science, that span the whole globe. And we do have, particularly in Amsterdam, where our university is located, really a center of rich connectivity. So we tend to have the possibility to experiment and try out the things we do across networks, across the globe. So there is also a specific need to be able to effectively experiment with these protocols in the field and not just in your research lab. And we in Amsterdam have the luxury of being able to do that. So this is partially also why we think we are fortunate to be able to present this work, because we have the environment where we can actually carry out the research. Now, why P4? I think I was invited here, so you're telling us you want to do a more transparent and more secure and more stable internet, not just for the operators, but also for the user, to support science, to support societal new emerging applications. And the question is, why P4? So I think what we actually started with, and some of the motivation for initial work, is that we saw that P4 was offering us advantages compared, for example, to out-of-band approaches. And in particular, when we started, we were looking at fine-grained telemetry. So the fact that we could do telemetry in a much more fine grain, not sampled, but on a per packet basis, and be able to get an insight of what's happening into the devices. So no need for summarizations, no need for sampling, where you can actually lose some of the information, and a wealth of data that can be used in many contexts. So this is where we started with. We decided that we wanted to effectively use P4 to enrich protocols that were going through, for example, our devices for additional telemetry, and be able to do it on a per packet level. And this is allowed to actually tackle some of the questions that we have for each one of these pillars. So the transparency, the security, and the stability. So in terms of transparency, if you can do P4 telemetry, you can actually look at what's happening into your network. And one of, for example, the examples work we've done, I'll have a slide later on also on this, is to have an insight on the path that your traffic has taken. So if you think a traditional sampling, when you're trying to see which way my flows are going, you might miss, because of sampling, elements on your path of where you're going. With P4, you can build a whole chain by effectively enriching existing protocol and follow your packet across the network. So you use P4 to put additional information, which you at the end are able to extract full information on path. So not a single device P4, but a chain of P4 devices. This is also maybe something interesting to think of, when you can actually control multiple P4 devices and look at the whole end-to-end path. If you can do this kind of telemetry, then you can also look at effectively uses this insight for security purposes. So again, if you look at how intrusion detection systems work and in which way they try to reconstruct, for example, where is the source of an attack once they have been identified as a malicious traffic. Again, if you have this kind of telemetry and you're able to see effectively which way the data that came into your network has come in, for example, relying indeed on the hop that they have gone through, you can enable security actions, or to make your network more secure. And another research we are exploring right now is that, again, through P4, again, through telemetry, through timestamping, so for example, timestamping or looking at effectively at the entry and the exit point of traffic through your devices, you can also have an insight, effectively an indirect insight on the how bottlenecks create through the network. This is again something that you can do on the whole network chain of P4 devices to see, do I have queues filling up, by looking at times when packets are leaving specific hops into the network. So I think maybe as a distinguishing point from previous presentation is that one of the interesting insight we have is that P4 can also be thought of a overarching programming language for an application across devices. So not just on the single device, but trying to obtain a behavior that moves across the whole chain. And this is something that we have done, and I can show you how we use P4. Maybe also this is an interesting insight also for discussion later. So when we started, we were using primarily software switches and compilers from p4.org. And then we moved to hardware. Now, the use of software switches and compilers, I want to mention it here. I have little asterisk, a little star. I still see it in the P4 space as a very useful starting point, for example, for education and student labs. So if you have any kind of educational program where you're actually trying to train the network engineers of the future, the network architect of the futures, having tools like the ones, the software switches allow them to actually see how this works. And maybe again, there will be people that will think, yes, I could actually scale it more easily to actually train people to use this kind of environment. Of course, at a certain point, we felt in our research, we absolutely needed to move to hardware for better performance. So we are using Barefoot switches. Also, one of the advantages of using P4 and looking at the whole P4 chain, let's call it a P4 chain, is also the true, for example, metronome NICs, smart NICs. You can bring the P4 capabilities all the way to the host. So if indeed you're interested in an application that monitors or does some kind of telemetry across the whole sequence of hops, it's important to also be able to start to do it at the very beginning of the path. And so this is the way we have been using P4. There's been an evolution in the way we have used the tools that we have at our hands, but still with the goal of answering those other more general questions. Now, I would not be an academic if I would not have a few references to papers. I'm not expecting anybody probably to go and read them, but just to show that there is work we have done that has been published and discussed in the research community. And it just repeats and gives a little bit more insight in some of the things we have done so far. So in terms of telemetry, as I said, up to now, and I will end with a slightly different tone, we have effectively looked at how do you enrich existing protocols through P4. So for example, you could have additional information in a P4, through P4, for example, in packet headers, that allows you to effectively follow the path of packets through the network. This is something that you could do indeed if you could control a full chain of P4 devices. You can do it in different ways. You could add a tag as you come into a device. You had say the identifier for the device. As you move, you keep this identification, and effectively you are not any longer in need of sampling each one, but when you get at the end to a collector, you just need to be able to carry out all this information and process which path have been followed by your packets. You could also do it in slightly different ways, and this article shows that you can actually tie the way the path has been followed by having knowledge of routing tables. So if you would have a way in which P4 can effectively tag the traffic that comes through the various devices by knowing what was the state of the routing table at the time, you can also reconstruct which one was the flow followed through the network. This is just to prove to the community, to the research community, and maybe indeed also other people outside the research community, that you can actually follow your traffic through P4 by having this kind of telemetry. I go back to the security aspect, which is the second one, is that the fact that also, again, if you can do it on the whole chain of devices and you have this kind of telemetry, you can try to recognize effectively traffic that comes through your devices. So for example, you can have implementations of Bloom filters in P4 to try to effectively count whether you've seen a certain amount of packets of a certain type, and effectively from that build profiles that allow you to identify some malicious behavior. And at the end, you use this P4 information to create a network that can react much more quicker to attacks. Of course, there is a whole kind of research that maybe is not relevant to this discussion today, that allows you from this telemetry to do all kind of forecasting and machine learning based on what is coming up into your network later. This is also a very interesting direction nowadays in networking. Try to see how much machine learning can help you in security. But P4 is again a building block that allows you to actually do that if you can actually again count very quickly what type of information is coming through. So also here there's been some work that we have done that maybe some people will be interested in reading and discussing later on. So finally, maybe this was my last slide. I want to move you to to what we also, I have a sort of a history of where we are now. And where we are now is that actually we are moving in using P4, not just to effectively enrich through telemetry existing protocols, but we are actually looking at P4 as a way to test new protocols, so future emerging infrastructure. So there is quite a lot of research in the community looking, for example, at new ways to do routing like Scion protocols that are being developed. And the question is, can you actually use P4 to do these experimentations of new protocols, again, on large scale across devices to try to see if this new protocol work. So where we are involved right now is an initiative called the Two-Stick, which is indeed about securing stable and transparent internet, which is in our case started as a national initiative where you have a P4 testbed across the country where you can do this kind of multi-site experimentations of new protocols. And the ambition is, again, because we want to have testing capabilities across multiple sites, is to extend this kind of P4 experimentations environment to beyond one university or one country, but across a whole range of parties in the United States, all over the world. So the way I see that the research has effectively moved is to just effectively leveraging P4 to do something more than what you would normally do. And now looking if you can use P4 across the site, across multiple sites, to experiment with really new protocols. Again, with the idea that ultimately this protocol will give you even more transparency, more security, more stability. So effectively is seeing the potential. We have learned the potential of P4 by starting, if you want, relatively smaller, and then now we are moving to actually to a larger scale to see can we really support new science use cases, so Untitled use cases with really new protocols that we develop in P4. So again, also on this, I have a little link to a blog we wrote to the whole testbed. So again, if somebody would want to be interested to read more, we can do it. And then again, I thank you for having invited me. I'm excited to discuss some of these things in the panel. And I also thank some of the collaborators that worked on this research.
Thank you so much, Paola. I mean, really loved your presentation and the work and the research that you're doing to make internet transparent, secure, and stable, and the role that P4 is playing in it. I've always thought, real-time telemetry is one of the killer apps for programmability, and it's great to see you and your team taking advantage of that to, to build a secure, stable, and transparent internet. Really cool stuff.
Great to be here with the panel of esteemed folks from academia and industry. So my name is Arkadiy Shapiro. I'm a product line manager responsible for software in the Barefoot division of Connectivity Group in Intel. And today I'm going to talk about the P4 programmable data plane use cases and essentially focus on how our customers, the customers of Barefoot pre-Intel and also, Barefoot division of Intel since our acquisition, are using P4 and using the programmable data planes that we offer. Now, to start off, what I would like to talk about is what are the building blocks of programmable data plane? It's not enough to just have the language or to just have the programmable ASIC, which we all do, but it's important to kind of highlight all of the building blocks that are essential to call yourself programmable and to call your solution as a programmable data plane solution, right? And number one is, of course, having an open programming language and a community around it. So here we're using P4, like both Paul and Guy talked about. It's a growing programming language, and the most important thing is the growing community around that language, right? Where the language is open and there aren't kind of proprietary aspects to that language. Having the compiler and the chip simulation model, right? Without a compiler, we wouldn't be anywhere, right? And there's portions of the compiler that are open source, and each vendor that uses the compiler, they typically write their own backend for their own silicon. Right? So compiler is hugely important. It's actually a very complicated piece to develop to have a compiler for P4. But we have been able to do that and have been shipping it for quite a few years. Third one is having a set of visualization tools. Once you compile your program, you really want to see how that program utilizes the resources of the chip, and perhaps have the tools to generate automatic tests for those programs to verify whether your data path is correct. So there's a lot of tooling that's required around just the basic compiler and drivers to be able to effectively use the programmable data plane. Right? Having flexible and auto-generated APIs, most commonly in a fixed function solution or fixed function silicon, the APIs are fixed. And if you're going to have programmable data planes, your APIs cannot be fixed. And your APIs from the lowest level, and also ideally from higher on up, have to be fully flexible and fully auto-generated. And of course, finally, having a fully programmable ASIC, which we have with Tofino and Tofino 2, and also from the ASICs that Guy talked about earlier. Now, starting off, kind of diving into each of these building blocks, in terms of Barefoot Tofino, which was the first ASIC that we released as part of Barefoot, this is a high-level diagram of the ASIC. It has a pipeline architecture with, depending on the configuration of the chip, in this case, it's 4 different pipelines. They're uniform pipelines with equal number of stages in each pipeline for ingress and egress. And in our case, having this pipeline architecture really allowed us to achieve uniform performance, predictable performance, and also have an architecture that's easy to design a compiler around of it, right? Where again having the pipeline and having all the stages of equal size. Right? So again, similar architecture we have for Tofino 2. We might have more stages, but each stage has the same kind of uniform size in terms of number of SRAM and TCAM blocks in it. Now, moving on to P4, I felt that it's important to highlight, why P4 is critical to this and why we really chose P4. But because sometimes I do hear from folks, well, you guys could have used Python or C, and I think Guy talked a little earlier about why they chose P4. But to kind of highlight this from my perspective, number one is the large open ecosystem around P4, right? Where with alternatives there, really is little to zero community, whether it's common languages or languages that are being designed specifically for data plane programming. Right? Having the target and architecture independence, right? Which is a very important tenet of P4. Right? Yes, like any language or any kind of technology solution, there are specific constructs in P4 to leverage kind of the most unique features of each individual hardware, right? Whether it's Tofino or NICs or FPGAs or other ASICs, but the core architecture of the language, the core tenets of the language are really high level and they're target independent, right? Which kind of brings up to the next point. Right? And finally, the language, as before, has been proven now for quite a few years and really has been designed for network pipeline programming. Right? The constructs of the language, right, such as tables and actions and fields, right? They're all kind of very much geared towards network pipeline programming, where traditional programming languages just don't have those constructs, which makes designing a programmable data plane solution a lot more difficult, kind of, with those solutions. Okay, so moving on, kind of how do you put things together? And this is a slide of what we have with a Baremetal switch ecosystem. Now, we also work with traditional OEM switching providers like folks like Cisco and others, where in those cases there might not be as much flexibility, but even we see with the traditional OEM vendors, they're now more flexible to put open source operating systems like Sonic on their switches. Right? But definitely in this kind of ecosystem, you have the most flexibility, and data plane programmability is really about having the flexibility, having the choice, and the choice doesn't just kind of imply having your own data plane, but also having your own building blocks to choose from, right? In terms of choosing the hardware and also choosing the control plane on top of it. Whether that control plane is open source control plane or a commercial control plane from kind of any one of these vendors. Now, the fun part becomes when you actually try to put things together and figure out, well, who's doing what. And as an example here, right, if you're trying to build a system with a Tofino ASIC, the data plane can be provided by any of these folks, right? Whether it's an ODM or Barefoot or end customer and some third-party consultant. Right? So, for example, let's say in this case, the end customer, right, the end user would be doing their own P4. And then, of course, we have to have a control plane. Typically, if you're doing your own data plane, you have to have control of the control plane, right? Because oftentimes, if you have a commercial control plane, whether it's from any of the vendors that I mentioned before, or from an OEM, they sort of own the data plane because they have to make sure that things kind of work together. There are some exceptions to that, but by and large, that seems to be true, right? So usually, if people want to have their own data plane, they tend to have their own control plane, which is either Sonic or Stratum, which is another operating system, or kind of something completely homegrown. Right? And of course, they would try to pick a system vendor, and the system vendor, for example, could be from EdgeCore Networks, or could be from Inventec, or any of the other ODMs or OEM vendors. In the case where the OEM, again, like Cisco, allows you to put Sonic on some of their switches. Okay. So that's sort of how the pieces come together. And in terms of the tools that we use to develop P4 programs, this is an architecture of our P4 Studio software development environment. I mentioned compiler being one of the key building blocks for programmability, as well as the APIs, right? So you'll see both of them here, where the compiler compiles program, loads the program either on the ASIC model or the hardware. The APIs get generated as well after that. And then there's information generated for Barefoot P4 Insight, which is a visualization tool to highlight how well the P4 program is using the chip resources. Okay? Now, of course, not everybody is ready to do the P4 program by themselves sometimes, or sometimes they might be ready to just modify the existing program, perhaps write bits and pieces, but for the most basic functionality, they might be using a higher level APIs, like SAI. Right? SAI is a common API. It's a fixed API. So, unless you're using something like SciFlex, SAI by itself is a fixed API that has to be developed, right? So for what typically we see from folks is for something like a top-of-rack switch application, they like to use SAI for the most basic functions, but for some more advanced functions, like let's say developed a switch, but on top of that, I'm doing something like NAT, or I'm doing a load balancer, some security application. Right? They might want to be using the lower level APIs because that gives them the most access to programmability of the chip. Okay. So moving on to use cases, here are some of the high-level use cases of data plane programmability, whether it's enhancing switching and routing, providing better telemetry, and better telemetry means that you really get to figure out what you're looking for, right, and what you're actually tracking, right? Because honestly, every solution out there has some form of telemetry. You don't have to have a programmable solution to have telemetry, but it's important to have a programmable solution to have the flexibility that the telemetry needs. Right? And oftentimes with the changing network requirements and applications, we often see that kind of a solution that's been developed by a fixed function chip later on becomes not sufficient enough. And at a high level, kind of looking at the benefits of the P4 programmable data planes and programmable switches, number one is reduced complexity. Really what we see folks is taking out things they don't need. Right? If they don't need something like tunnels or NAT or some other kind of more complex applications, they just get to remove those and leverage the data plane for what is needed. Right? And that's both goes for end customers and also for OEMs, right? Where they're providing multiple profiles that are really geared towards a specific networking use case, as opposed to having a generic top of rack switch that can sort of do it all, right? And perhaps if you cannot do it all, then for a different type of use case, well, you build a different top of rack switch, right? So that's certainly not the case here, right? Doing things like future proofing, of course, whatever new applications or new features come out, you just develop new P4 programs, right? Doing it, quickly, right? Doing it at the speed of software, of course. And then I talked about data plane telemetry already, and scale is pretty important one. We really see particularly hyperscale customers, ones that kind of manage big and expansive data centers, tend to use programmability to focus on the scale, but the scale that they need, right? Whether it's tunnel scale or NAT scale or IPv4 scale or IPv6 scale, right? Oftentimes when you need one, you generally don't need the other, right? And when somebody kind of tells you that they need both, more often than not is usually they do it because of an insurance, not because of the fact that they really know the network. And again, P4 programmability and data plane programmability is really about fit for purpose networking, not about building something that kind of fits every single use case in a one data plane. So I talked a little bit about scaling. This is an example of maybe a more high-level example of somebody focusing on scale. And in one case, they focused on kind of host routing for IPv4 because potentially that was a top of rack switch. And in another case, they really focused on longest prefix match routing. Right? And they've configured the data plane for both v4 and v6 to really kind of take advantage of that. Right? Depending on where you are in the network, what type of routes you have, kind of this was pretty flexible to do, right? Whether they did it for v4 or v6 or for host routes or for longest prefix matches. Now, next use case is cloud gateways. We do tend to see a lot of customers who are faced with a dilemma. They actually have a lot of cloud gateways, which are really running on servers. Now they've been able to squeeze as much of those servers as they could by using things like DPDK, and myself being from Intel, we absolutely love DPDK. But the fact of the matter is that still no single server can contend with the speed of a switching ASIC, right? That runs up to 6.5 terabits or up to 12.9 terabits per second, right? Depending on the generation of the chip that we have, right? So the customer was really looking forward to migrate the application from servers to switching silicon and kind of have that data plane acceleration. So what they've done is they've actually designed their own data plane to do this v6 Jerry gateway. They actually have multiple variants of gateways depending on where the device sits in the network. Sometimes they do like a VXLAN to GRE translation. Sometimes it's like v4 to v6. They've taken the white box switch, used Open Network Linux as a base, and kind of wrote some control plane code together with FRR on top of that. As I said, again, they had a custom P416 data plane that integrated with their own custom SDN controller. Right? And by the end of it, the benefits that they got was, of course, higher performance and have more flexibility and control because now they control the entire data plane. They can do or configure it to do whatever application that they desire. The next scenario is Baremetal server hosting, and this one kind of relates a little bit towards scale. In this case, what Baremetal server hosting means is essentially in a cloud environment, you connect Baremetal non-virtualized servers. Most cloud providers offer that as a service today, so they don't just offer you to put in VMs or containers on perhaps their own operating system, but you really get to have a Baremetal server to do whatever you desire. But the challenge is, of course, if you try to connect the Baremetal server to a virtualized workload, you need to have some tunneling involved to be able to do that. And while all switches can do tunneling in VXLAN, right? That's why this was a multi-vendor demo where you have a bunch of top-of-rack switches right here from both Barefoot Intel, but also from Mellanox and Broadcom. The key thing here is the scale that you can achieve with a programmable switch. A similar type of switch that's certainly not compared from a fixed function device, right? And oftentimes what we see is that when you're trying to integrate with a cloud SDN controller, the way that the VXLAN done is not always so standard, right? Because VXLAN is just an encapsulation, and what cloud vendors typically like to do is they try to adapt it towards their own use cases. And having a programmable data plane really allows them to just treat VXLAN as encapsulation and then deal with VXLAN, for example, the way that they want to, right? To program the tables the way that they want to not have to have any kind of quirky workarounds because of the fixed function chip implementing VXLAN in a certain way. Right? So that's really where the power of programmability comes in this particular kind of a cloud Baremetal server hosting scenario. Okay. So next scenario is network packet brokers. We do see kind of quite an explosion of customers building packet brokers with programmable data plane for probably one key reason is the data plane and API simplification. Right? In the past, if you're trying to develop a packet broker, you would typically use either a fixed function chip where you can build a solution, but you can go for quite a few workarounds and hacks in order to make that happen because the chip was simply not designed to do that. The chip was designed to do data center switching, like top of rack or spine switch, but certainly not doing a network packet broker, which is a very different type of application, right? For those of you who are not familiar, packet broker is a parallel network that many customers build around their production network, where the traffic is copied, right? Whether it's tap or span, sent into packet broker network. And essentially, the traffic goes unidirectionally towards a monitoring systems that connected on the other end of the packet broker network. Right? So in this case, what these customers and vendors as well as end users, you'll see a kind of a mix of them, have been able to do is they've configured the data plane to just do that, right? Not do typical layer 2, layer 3 switching, not do typical tunneling, but focused on the packet broker functions, right? Get the packet, apply a policy, and decide where the packet should go. And as well, do some interesting things like stripping headers in a very flexible way. Again, today, still, can you strip some headers in the fixed function chip and a fixed function solution? Yes, you can. But can you do it in the most flexible way? Probably not. And again, in order to do that, folks tend to resort to a lower performant kind of a server or FPGA solutions. Right. So in this case, those vendors have been quite flexible and achieve whatever header stripping they want. Slicing of packets, which reduces the load on end monitoring servers. Encapsulating or decapsulating tunnels. Probably in this case, the more common thing is decapsulation, because when the tunnel traffic comes in, you want to remove some of those headers again to reduce the load on monitoring servers. Having very flexible load sharing, and of course carving out your TCAM tables specifically for these policies, right? Because the network packet broker is a policy-driven network, right? So as I said, right, lots of interest from folks designing packet brokers. Oftentimes, this is something that very simple that people can start with before they design a more complex P4 application. But something as simple already brings them tremendous benefits and tremendous cost savings, because particularly for some of these end users like SK Telecom and KPN, they can now actually try to build their own solution and reduce reliance on a kind of a proprietary vendor implementations. And finally, the final use case is emerging technologies. There are a couple of scenarios here. One is segment routing v6. Now, segment routing has been talked about for quite some time, quite a few years, but it's still not a technology that's set in stone. There are still new RFCs coming out. There's some debate about various kind of aspects of SRv6, which would undoubtedly mean that the data plane will have to change, and that the fixed function chips of today that do support SRv6 may not be able to support the new variants of SRv6 in the future. Okay, and just as we've proven initially that we could do SRv6 when few chips could do it, we're going to continue to do that today. Okay. And the other scenario that's maybe important to point out is large-scale PVPoE session termination. While PVPoE is not necessarily a new protocol, it's been around for quite some time, it is impressive to be able to do that on a data center class switch, where typically you don't design those protocols in a fixed function chip for that type of use case, right? But in a scenario where telecom operators are trying to re-architect their central offices as data centers, right? So folks might have heard of a solution, Core. They're trying to really have a top-of-rack switch there, but on top of the traditional switching function, also have functionality of PVPoE termination. Okay? So that's what one of our customers have done. Actually, a couple of customers have done. So with that, I'll conclude my presentation. I'll hand it off to Prem.
Thank you so much, Arkadiy. Really enjoyed that presentation and the use cases and your software framework and everything that you described. So thank you so much. So I have a couple of questions for the distinguished panelists. I'll start with Paola. Paola, thank you so much for that wonderful presentation and the work that you're doing to make internet better. You've described, certain pieces of technology that you've used in terms of switching and NICs, and of course, P4 programmability. But I was wondering if you were using any other pieces of open source software together with the devices and P4 compilers that you were using to basically build this network and achieve the research that you're doing. If you could speak a little bit about that.
Yes, I can tell you something about the research we have done so far, the way we've used it in the past, and also where we are looking at the future to have more usable ways to do what we do. The first thing I have to say that so far we've done quite a lot of in-house control plane, data plane communication, which I guess this is the part you're referring to. For us, because of the dependency on each target device on P4, so the fact that the communication is dependent on the target you're going to, and in every piece of research I present you, we use different targets. We built our own programs, so effectively use combination of Python and Scapy and Thrift. But what I think we're looking forward to work more with is P4 runtime, because we would actually allows us to actually still use an open source solution to have the standardizations of the communication between control and data plane. So I think this is the way we are moving. We want also to not have to do ourselves that part of communication, control plane, data plane, but to have something where we can reuse components for every kind of P4 program we write for our use cases. So I guess this is a little bit direction where we are moving. As you've seen also before, when I presented our evolution of work, we started to work more with the software switches, open source software switches, and we moved to hardware. In the same manner, we want to move from having our own local to P4 runtime.
Excellent, excellent. Now, any of the work and any of the P4 programs and associated pieces of software that you're developing, are there plans to contribute it back to the open source society or leverage more from the open source society? Is there any areas that we're looking into?
I think we want to contribute more. As academic, we are always open. Our research is publicly funded, so we are expected to contribute back. And I think we have always made our software available, and the work of our students, so the work of our researcher is publicly available. I actually found very interesting in Arkadiy's presentation some of the last use cases he presented, because one of the things we are looking at, which was not in my presentation, is, for example, the integration of P4 and segment routing. I told you that we see the evolutions of the internet going toward control, virtual network functions. So, for example, we are now looking at segment routing as being an enabler for control toward network virtual functions. So the integration with P4 is also something that we certainly look at and we will share with the community. So this is, again, a direction of work which I think is promising. And I'm pretty sure there are people in the audience watching this video that probably are thinking to do the same kind of things.
That's true, that's true. Yeah, segment routing v6 is really cool, and the applications to simplify the network and have more control and more visibility is pretty exciting. Guy, a quick question for you. I know segment routing v6, Cisco is pretty active in the segment routing v6 arena. Are you guys doing something in this area? So specifically related to segment routing v6, and then a follow-on question would be, you know, in terms of leveraging some of the open source software related to P4, how are you doing it, and anything you plan to contribute back, that would be good to know.
Okay, so that was two parts.
Yes.
Okay, so I think that if you ask me about any protocol out there, is Cisco doing anything about protocol X? I would say yes.
Yeah.
Okay, so specifically for SRv6, there is a lot of work being done. I think, at least from the small prism that I know, in all aspects, from implementation all the way through to standardization and contributing to the standards. So that's high level. Of course, in Silicon One, we have extensive support for SRv6 and the emerging flavors of SRv6. I would say that the support is not in the hardware, it is more in the microcode or the P4 code we are writing. Again, we are programmable.
Yep.
Okay. Of course, there are hardware limitations. For example, you cannot add 500 SRv6 labels, taking it to the extreme. But this is stuff that there is work on in Cisco. So that was your first question.
Yes.
Regarding open source code, I do not, again, Cisco is a commercial company, and I do not know what the inclusion of open source code in our proprietary code, what are the legal implications, sorry. So we haven't taken pieces of code from the open source community and used it in our development. Also, programmability, the device architecture, and then the compiler, and then the language is just the bottom of the stack. You then have the application stack. And even there you have many concepts and objects and definitions that you define in order to model the application that you are doing. And again, this is some of the added value that we as Cisco provide, the cohesive view of networking. That's the way I see it. And what we saw in the open source community are different models, different concepts that do not always fit. I can tell you that we look at open source code and we learn from it and we compare ourselves to it. But again, I think that both from a legal aspect and also from an implementation or a practical aspect, I don't think that the open source code is at the level that that at least the stuff that I'm working on we can use.
No, that's absolutely okay, and that's the beauty of open source, projects, right? Like, and you can learn from it. You can either leverage it directly, or take some principles and concepts from it and use it in your products, and that's great to see. And the choice is actually with the implementation, the people who are doing the implementation. So that's great. That's good to know. So Arkadiy, how about your team? Have you guys done anything in the open source ecosystem with regards to P4? What do you see any benefits to doing it? And just curious about your work.
Sure. So I think from the core of the P4 Studio software development environment comes from the open source. So a big piece of the compiler, the front end of the compiler that does the language interpretation is fully taken from open source. And anything that we change in that, like let's say we propose a new kind of enhancement to the language, we would upstream it back. I would say that both Barefoot before Intel acquisition and with Intel and myself personally, I believe that it is important when you're doing this type of work to kind of contribute it back to open source, because otherwise you can't call yourself a programmable data plane solution, because if everything becomes proprietary, and it's very easy to start within something that's open source, and you were saying that the P4 language is open source, but very quickly it becomes totally unrecognizable because you've added all that stuff to the language, to the core definitions of the language, kind of how the compiler first interpreted that people would not recognize it. So from that end, we leverage what's there and we kind of contribute back, both in terms of the compiler definition, but also from basic P4 program examples that exist in the P4 line, right? Now, I think, we're talking about before here, but we have a lot of open source work in other open source projects like SAI and Sonic, which are no less important because without the control plane, data plane by itself is not going to do anything. So contributing to those projects and kind of leveraging those projects is super critical to design a complete solution. And because in our view, if the control plane doesn't remain flexible enough, you really can't leverage a lot from the data plane. And then what happens is that folks tend to not be able to leverage as much of that open source control plane as possible to design a good solution with programmable data plane, right? Because then the control plane is really designed towards a fixed solution, not a programmable solution. So yeah, that's what I would say on the open source topic.
No, yeah, this is great to see, right? I'm really loving this discussion because there's multiple different architectures in terms of target architectures. Like Guy was explaining about how they've leveraged P4 for a run to complete architecture, and Arkadiy, you've explained how you've leveraged P4 for a pipeline architecture. I mean, shows the flexibility and the adaptability of the concepts and the programming language. So that's quite powerful. And I know Cisco is actually contributing in language design working group and P4 apps working group. I know Cisco is a large company and they have other teams contributing. So it's really great to see their participation and in making the language and the community better. So one other question for Paola. It's really fascinating to see the research that you're doing and the concepts of transparency, security being brought to internet. Are you looking to kind of take this work into like some kind of industry partnerships and taking it and getting it deployed and tested in real networks? I know you have some efforts going on in that arena too, right, Paola?
Yes, so thanks for the question, because it's a question I like, is that I don't want to give the impression we do this academic work which stays within the university or within our students. We reach out for the work we do, and as you said, we have a number of projects particularly related to the concept of data sharing, where transparency and control and guarantees of privacy are very important with industrial partners. So these projects are usually, indeed, they have a scientific component, but they also see industrial partners collaborating with us. So for example, we in the Netherlands work in a project with KLM, which is the KLM Air France, the airline company. And together also, for example, with Siena Networks, with Siena in the United States. And there we look at how you take this programmability aspect, this programmable infrastructure, to be able to share data between airline companies. So for example, engine manufacturer might want to share part of the data in a secure manner, in a controllable manner with the airline that is using their airplanes. So this is one example. Another example where we also have industrial partnership is, for example, in the health sector. In the Netherlands, Philips is very big in the health arena. And also there you see that programmability, a programmable network that allows you to actually decide where the data goes, who can see the data, who has access to the data, can then transport it or moved to the health use case. So I would say that most of our collaborations in terms of programmability usually look upward toward the application and then find industrial partners that are interested in having secure data sharing. And the way we allow that to happen is by having these programmable infrastructures. So really for us, programmable infrastructure is a mean to actually achieve this higher goal of secure data sharing, for example.
Oh, that's excellent. I personally think secure data sharing and security and transparency will become super important for the functioning of the internet. I mean,
certainly in Europe, where you have all these GDPR regulations, where you have actually be able to see who has had access to the data, or what are certain of the legal implications of sharing the data. Also, in some sense, also digital sovereignty, which is also a discussion that you hear more and more in the environment around you. It's something that you can actually, how do you say, support by having programmable networks. So digital sovereignty in a specific use case is relying on programmability to achieve its intended goal. So yes, I think programmability opens up lots of opportunities at the application level, which is also what I try to actually convey in my presentation.
That's excellent. That's excellent. Yeah. Now, looking at the device vendors and the ASIC vendors that are P4 programmable and the needs of the internet, I feel like we're at an inflection point for being able to take advantage of these technologies and build a better internet and make the future of internet more transparent and secure and so on. So this is really great. Guy, do you have any thoughts, closing thoughts?
So let me continue on what you said. Yeah. I think, if I look at what Intel and Barefoot are doing, if I look at what I see Broadcom is also trying to do, if I look at what we are doing, I think that the industry is at a stage where we see many programmable devices. Now we can argue about the efficiency and the power consumption and the level of programmability and the table sizes and all the, and we can say this device is better, this device is not as good. But I think that the industry, if I look at the last 10 years, is understanding, is at the stage where devices are programmable. We no longer really need fixed function ASICs. And the challenge now, on the one hand, is to make them more efficient than they are, but it is to define the applications that we can do with them. Now, like Paola said, telemetry, in-band telemetry, security. If you look at what's going on, there are many solutions for each of these cases. Even within Cisco, we see several, like I said, Cisco is doing everything, right? So we see a lot of protocols and approaches, both at the data plane level and the control level, et cetera, et cetera. And I think that the industry's challenge is to define the place, the direction where everybody should move to, so that we have not a single telemetry solution by vendor X and a different one from vendor Y, but that vendor X, Y, and Z all work together. Now, with programmability, it becomes easier. We don't have to wait for the life cycle of a fixed function ASIC to achieve it. Okay, we can shorten the cycle, but I think that is the challenge because, again, Paola is doing research in direction X and Cisco is defining protocols in direction Y, but in order for all the systems around the world to work together, we need to find the common or the shared functionality. And I think that is the big challenge that's looking forward.
No, a big challenge and a great opportunity too. So that's really exciting. Arkadiy, any closing thoughts?
Yeah, I definitely share some of the challenges that the other folks have mentioned. And yeah, from my side, just to reiterate that the challenge is really to have a flexible enough control plane to leverage all of that programmable data plane. Because if the control plane remains to be kind of very monolithic, which is the case still in many operating systems today, you really cannot do a whole lot, and that really means that for an average person, not somebody as smart as Guy and Paula, but for an average person, programmability kind of still remains a little bit elusive and a little bit more difficult. And I think the big challenge, at least of my work as a product manager, is how do we make it easier for people to achieve, right? How do we make it as easy as programming a computer, as easy as writing a C or C++ program or a Python script, right? It's definitely a heck of a lot easier than programming some microcode or maybe doing Verilog. That's at least the feedback that I get from customers. But I do have to contend that it's certainly not easy enough, not as easy as what we would like it to be.
No, that's true. We're also seeing, I mean, this is a different domain, right? If you look at a typical application developer, they probably have an x86 PC, they're able to compile in C, and it's easier for them to learn application development in these compute and graphics-oriented type of, development environments. But, networking is a different domain. The constructs are different. But I truly believe with the advent of P4, it has actually become a little bit more easier for people to understand packet processing concepts and learn how to express packet processing behavior and build new applications. So that's pretty cool. And I think sometime in the future, it'll become, part of any application development, because the future is going to be distributed, connected compute. I mean, it's already like that. So connectivity and, shuttling packets will be taken into account in application development and so on. So this is great. I'm very thankful for this discussion. But before we close, any final thoughts from you, Paola?
Yes, maybe I will attach to your last remark that I really do see also the role of academia, or in general of higher education, to form the professionals of the future that are able to work in these new paradigms. So I really do see also the need for a shift in the way we train people, we expose people to these new ways of working. And again, maybe the also related to the previous question, the open source community, or the ability to do training for younger generations on open switches and the open software allows them then to acquire all the tools that they will need when they go into the market. Because we need also different type of people. It's not just different type of hardware. It's not just different type of code or languages. It's also the people that use it. And I think that's a shift that also is happening and will happen even more in the future.
That's absolutely true. I want to share an experience that I had in Amsterdam last year. I was at KPN and there was a P4 hackathon, and it was fascinating to see like really young, bachelor's students together with like, senior network architects at, those are building large networks, get together and hack up a P4 application together and then present it 2 hours later. In the morning, there was a P4, training. It was more of a discussion. People already knew P4, but they were just like asking questions. And then in the afternoon, they took 2 hours and went developed a few interesting, P4 applications and presented it in the evening and put it out on the GitHub. So yeah, I was fascinated when I saw that, and truly, this is going to unlock some really powerful benefits for the future of internet. And I want to thank you for all the work that you all are doing, Guy and Arkadiy, in bringing programmable data planes to the market, and Paola in taking advantage of these things and making the internet better. So thank you so much for your time, and I really enjoyed it and hope you did too. And I hope the viewers will enjoy this too. So thank you so much.
Good.
Thank you.
Thank you, everyone.
Thank you. Thanks a lot.